Hey guys, happy Valentine's Day. We did not get a chance to really cover the notes too much today. Several of you were actually absent, and so it just would seem best to go ahead and make this video. This is a brief set of notes. As you can see, I'm not in my home tonight. I'm actually still here in Hazard. I'm at the Hampton Inn and Suites. Because on Valentine's Day, apparently I get to hang out at a hotel while Steven hangs out with some of his buddies and uh, gets to go out and have a good time. Just been doing whatever. And my wife is back home taking care of our dogs. And we just had two goats born tonight, too. So she's trying to round them up and take care of them as well. So this is my Valentine's Day. I get to do math with you, you fine, fine, wonderful people. We're talking about mathematical models. This is not too challenging. It requires a lot of thought, though. You just have to be really careful with what you're doing to make sure that you are solving these problems correctly. Don't just rush into it thinking that it's going to be some formulaic process every single time. You really have to consider what information you're given. So we're going to jump right in with the first example. It says let P equals some point xy, and let that be a point that's on the graph of y equals x squared minus 1. Part A asks you to express the distance from P to the origin as a function of x. Well, that sounds like a lot of, I guess we'll say jibber jabber, but it's really not that bad. I'm going to go ahead and start out for part A right here. We know that the origin is the point 0, 0. And if I'm using this as a function of x, we know that point P, we have an x value of x, and the corresponding y value is actually defined by our function, which is x squared minus 1. So whatever I put in for x squared minus 1 gives me my corresponding y value. So that gives us the distance formula, if you guys recall, is the difference in the x values. So I'm going to get x minus 0 quantity squared plus the difference in the y values, which will be x squared minus 1 minus 0 quantity squared. And then when we simplify that, we get x squared plus x squared minus 1 quantity squared. So we can leave it like this. That's our distance for any given value of x, or we can clean it up a little bit more if we'd like. That would give us x squared. When we expand the x squared minus 1 quantity squared, we get x to the 4th minus 2x squared plus 1, which further simplifies to x to the 4th minus x squared plus 1. So I will let you get away with this if you would like, but I would much rather prefer you get to this point. Either one will give you the exact same answer for any given value of x. So our distance formula is either one of the two that I've circled here in pink. Again, like I said, I would prefer the bottom one where you have the square root of x to the 4th minus x squared plus 1. But either one's still going to work. So for part B, it says what's the distance if x is equal to 0? So we take that distance formula that we just computed and we substitute 0 in for x, which simplifies to the square root of 1, which is just 1. So the distance when x is 0 to that point on the graph is just going to be 1 unit. So we do the same thing for part C. We substitute in our value of x, which happens to be 1 in this case, so it's 1 to the 4th minus 1 squared plus 1, which is still going to be the square root of 1, so it's 1 unit again. And then our final component of this is what's the distance if x is equal to radical 2 over 2. I'll do that one in orange. And we get the square root of radical 2 over 2 to the 4th power plus, minus radical 2 over 2 squared plus 1. Radical 2 over 2 to the fourth power is going to be, let's see, 2, 4 over 16, which is 1/4. So we get 1/4 right here. And then radical 2 over 2 is going to be 1/2. And then we get plus 1. Make sure that I'm right on that. Let's see. 2, 4 over 16. Yeah, okay. So 1/4 minus 1/2 is negative 1/4. Negative 1/4 plus 1 is going to be 3/4. So the distance when x is radical 2 over 2 is 3/4 units from the origin. When we look at, we scroll on down here, we get another example, example 2. We're given this unusual configuration where we're actually wanting to consider a formula or an equation, which is y equals 25 minus x squared. And we've drawn this rectangle inside of that where we have one of the corners is at the origin. Then we move, we scroll up just a little bit, try to fit all this in here. So then we move x units to the right, and there's our second vertex. And then what we have right here is we move y units, which y is the same as 25 minus x squared. So we move 25 minus x squared units up, and that gives us our third vertex. And we still have this distance is also going to be x. So we've kind of labeled this rectangle for part A, asking us to express the area of the rectangle as a function of x. Well, we are very familiar with the area of a rectangle. It's length times width. In this particular case, my length is x and my width is 25 minus x squared. When I multiply that out, I get 25x minus x cubed. That is my area function of the rectangle that is bound between or bounded beneath this parabola that you see on the screen right here. So part B, what's the domain of A? Well, the domain is all the potential x values that this graph can possibly take. And so it starts here at 0. I'm going to erase my marks right here. Starts here at 0, and then it goes out here to 5 on the x-axis. Now it can't actually be 5, because if it were 5 inclusive, then it would just be a line across the x-axis, which is not a rectangle. So our domain actually is going to be all x such that x is greater than 0 but less than 5. It can be any number between 0 and 5, but it cannot include 0 and 5, because if it was 0, it would be just a singular point at the origin. If it's 5, then it's just going to be a line along the x-axis from 0 to 5, which is, like I said, not a rectangle. So it has to be between 0 and 5, just not including 0 and 5. If we were to graph the area function 25x minus x cubed, I've already got my calculator pulled up here. If I can get it to work. So we have 25x minus x cubed. We can ignore all the values to the left of the y-axis, because we don't need negative values for x, because we wouldn't. That would be it's irrelevant in this case. We're only looking at the positive x-axis. So if we wanted to zoom, let's see. Let's first zoom. Whoops. Zoom to the first quadrant. So you can see this graph. It goes up off the screen, and then it starts to come back down. But we can zoom out a little bit more maybe and get a better picture here of what we're looking at. There we go. Let me zoom box here so we can make it a little bit cleaner. Okay, so that's what we're interested in. This is the parts of the graph that we're most interested in for this particular problem. So when I go back to, that's part C, so we don't have to sketch that on the notes here. Part D says, for what value of x is the area the largest? So let's go back to our calculator. What value of x is the area the largest? That's at the vertex of this peak on the graph that we see right here. So to evaluate that using the calculator, it's menu, analyze, and since that peak is a maximum value, we're going to go to maximum, and we'll highlight it here. So when x is 2.89 units long, then the maximum area happens to be 48.1 square units. So for what value of x is the area the largest? That is part D. X equals 2.89 units. And if the question went on to ask us what's the maximum area, it would have been the corresponding y value that we saw on the calculator there, 48.1 square units. The last one, again, this is just an example intensive set of notes. It's just a matter of understanding what you're looking at and setting things up. We have two planes flying at the same altitude or headed towards one another. One plane is flying due south at a ground speed of 400 miles per hour. So let's draw that out for part A. It says build a model that expresses the distance. So this one plane is flying due south at 400 miles per hour, and it is currently 600 miles from the possible intersection point of the two airplanes that we're talking about right here. And then the second plane, let's see, the other plane is flying due west with a ground speed of 250 miles per hour. And it is 400 miles from the intersection point. Build a model that expresses the distance between the planes as a function of time t. So the distance between the planes would be the hypotenuse of this triangle, and that hypotenuse is constantly changing. So remember the hypotenuse of any triangle, we use the Pythagorean theorem, a squared plus b squared equals c squared, where a and b are the legs of the triangle. So let's consider the vertical component here, the plane that's flying south. The length of that leg of the triangle is 600 miles long minus 400 miles per hour. So at any given time, it's 600 minus 400t. That's the length of that leg of the triangle at any point in time. The same is true for the plane that's flying west. It's 400 miles minus 250 miles per hour at any given point in time. So that gives us the legs of our triangle. C is the distance, so we have d squared, that's the hypotenuse, is equal to 600 minus 400t. We're just substituting in the length of each leg, and then we have plus 400 minus 250t squared. Take the square root of both sides, and there's our distance between the planes at any point in time. Whatever t happens to be, we'll know exactly how far apart those two planes are. It's not it's just the distance formula derived from Pythagorean theorem. It just takes some thought. You just need to understand how to come up with the two legs of the triangle. I hope it makes sense when you have a certain distance. If you're driving a car from the high school to McDonald's, we'll say that's a mile. and you're traveling at 35 miles per hour. So that 1 mile gets reduced by 35 miles depending upon how much time has been taken up. If it's 1 minute, since the speed is in miles per hour, so now we're looking at 1 minute is equivalent of 1/60th of an hour. So it would be 1 mile minus 35 times 1/60th, and that would tell you how far you are, how much closer you are to McDonald's. We'll talk about this some more in class together on Monday or Tuesday rather, because I don't see you guys on Monday. But I may touch on it briefly on Monday before you all go to the library. But anyway, so I'm rambling. Here is a line through our equation, which I did not mean to do. This is our distance equation for part A. That's all we had to come up with. We don't have to simplify that any further. That's it. We have the distance equation. Part B says use a graphing utility to graph the distance equation. How close do the planes come to one another, and at what times are the planes the closest? So we're going to go back to our calculator and graph this. Let's see. We just do a new document. That'll be easier if I can get it to work. Well, it doesn't want to work, so let's just go and do a new document. No. Go to our graph. So we have the square root of 600, wrote it down, minus 400x, since the calculator is looking at this in terms of x, quantity squared, plus, what was it, 400 minus 250x, quantity squared. So we can't see our graph on here because it's a larger graph than our viewing window. So let's zoom out till we see this guy. Right here it is. And I'm going to have to change my viewing window a little bit more. So let's zoom. Let's do a zoom box. Maybe that'll help. Wow, I have totally messed that up. Okay. Let's see if I can manipulate this enough. Okay, so there's that vertex is what I'm looking for. So I want to since that vertex is the trough, we're going to do analyze graph. We want to look at minimum, and we get at x when x is 1.53, so that's our time. So at 1 hour and 53 minutes into their flight, both planes at 1 hour and 53 minutes into each of their respective flights, both of those planes come within 21.2 miles of one another. That's what information we can get from looking at the vertex of this graph. I believe that is the last example that was on here. Yes, it is. So we have these, let's see, seven problems that I'd like for you guys to take a look at. Remember, there was no quiz today. Your first exam is next week, so please look at this sometime over this weekend. If you have questions, at least look at some of the practice problems. Send me a message, ask me questions. I will be more than happy to help you guys. I hope everybody has a wonderful Valentine's Day, and I will talk to you on Monday. You guys take care.